All right, hi guys, how you doing? I'm super sad that I'm not with you today, but I am instead learning all about being a math teacher, which I'm excited about. And I will be back with you tomorrow. But today we're just going to finish that note for Friday. Now, in the interest of full disclosure, this is my not first, not second, but third time recording this because I have managed to not turn my microphone on, not once, but twice. So I'm hoping the third time is a charm, but I'm also hoping that that I don't have to do this again. So here we go. So we've started talking about chemical reactions, and today I want to be really clear. We're going to look at specific examples of reactions and types of reactions. Right? And what we're going to try to do is learn some general rules, and then I'm going to show you some of the specific examples I want you to know. So first we're going to talk about the simplest reactions, right, that you learned last year, and you should know this, but even if not, synthesis reactions is where we take two species, and I know it says compounds, but that wasn't the best choice of words. Where two species join together to form a single compound. Right, and let's just look. This is especially easy when we're talking about binary compounds. All right, so let's look at just a simple example. If I had magnesium metal reacting with chlorine, that would be a synthesis reaction because we have two single species, magnesium and chlorine, and they're going to come together to make a new thing. So magnesium looks like what? Well, of course, it's just Mg, and that is a solid. And that's going to react with chlorine, and that's a gas. And I know that that Blaze and Kevin, those, they're wild and crazy back there, Blaze and Kevin, they are yelling at me that I need to put a 2 here. Because chlorine, of course, is diatomic. In nature, we always find it in pairs like that. So now, when these react, what are they going to do? Well, they're going to make a compound. And because this is a metal and a non-metal, we know what kind of compound they're going to make. They're going to make, yeah, an ionic compound. Good. Specifically, they're going to make magnesium chloride. That's the only thing they can make. Because we know what happens when a metal and non-metal come together. They can only come together in one way. And what charge does magnesium take? Magnesium will be there, and it takes a 2+ charge. Good. And chlorine takes what charge? -1. So now what do I need? Well, I need 2 of these, right? So the negative charge balances the positive charge. And so what we'll get, the formula of our product will be MgCl2. That's actually going to be a solid. And we, of course, always have to make sure our equations are balanced. Is this equation balanced? Take a moment and take a look. And, of course, it is. So there we go. So now they follow a really simple form, which is, as a rule, we take something A and we add it to something B, and we get some new thing. And some textbooks you'll see this written as AB, some you'll see it written as C. Either is fine. I'm going to put C. But basically, two things come together and they make a single thing. There are some more tricky examples. When you do the homework, you'll see some that are not as simple as that. But in general, especially if it's a metal and non-metal, we just get an ionic compound. So for example, stick with that, I want to look at a couple key examples. And we're going to talk about these, and it may be a little confusing, but just bear with me. So what will be easy? Well, we always said when a metal and non-metal react, it's just going to be ionic. So if we did a metal and oxygen, we're going to end up getting a metal oxide. A metal oxide. Makes sense, right? So let's look at an example. Let's say, oh, I don't know, sodium, which is a solid, reacts with oxygen, which is a gas. And of course, at this point, let's say Kendra is saying, Orlando, you fool, you've forgotten the 2. And I will say, Kendra, you are right. And we will put it in there. So sodium and oxygen react, and we're just going to get the only thing we could get, because this is a metal and non-metal, it's got to be ionic. And so we can just go over here and we can say, well, wait a minute. Sodium takes what charge? Sodium's going to take a positive charge. And oxygen takes what charge? No, it's going to take 2 negative. And so what do we need? Well, it's going to take 2 of these to make it work, right? That positive needs to be doubled if it's going to cancel the negative. And so the product will be Na2O. Now take a minute and see if you can balance this one. You can pause the video. I'll assume that you paused the video and we're back. And I'll assume that you've all done a great job, but let's take a look. It may be tempting just to put a 2 in front of here. Now I have 2 sodium and 2 sodium. But that won't work because here I have 2 oxygen, and here I only have 1 oxygen. So I've got to slow my roll here, and if I have 2 oxygen here and only 1 here, I'm going to need to double this. And now, oxygen and sodium. Now on the left side, I have got 2 oxygens. On the right side, I've got 2 oxygens. So I'm good. Sodium, of course, right now I've got 1 on the left side. But I've got how many over here? Well, there's 2 in each of these compounds, and I've got 2 of them for a total of 4. Well, so that doesn't work. So I need to put a number 4 in front of sodium there. So hopefully that came to you. Hopefully you were able to balance that. If not, that's okay. Just make sure you get more practice. But now I do want to give you a rule. And there's a reason we're doing this, which is we're going to do some labs where we make metal oxides like this. So we just made a metal oxide. Right? And in this case, the metal is sodium, so we made sodium oxide. But there's something we want to know, which is that we can always take a metal oxide and we can dissolve it in water. And we're going to actually react it with water. So they react with water. And when they do that, they make bases. Right? And if you want to remember from grade 10, a base is a hydroxide. Anything with an OH minus ion, any hydroxide, that's an example of the simplest bases. And for the purpose of this course so far, the only bases we know. Again, the reason we're mentioning this specific case is that we are going to take that metal oxide, and in a lab, we're actually going to use it to make a base. So we have to know how that works. We can take any metal oxide. Here we're going to stick with the one we have, which is sodium oxide. And when we react it with water, it's going to make a base. And remember, we said a base, a hydroxide. So in this case, sodium oxide is going to become sodium hydroxide. And if we have to come over here, we can do that. We can say, okay, Na has a charge of +1, and the hydroxide ion has a charge of -1. So the formula of my base will just be NaOH. And now take a minute and see if you can balance that. Okay, and hopefully you'll see that since we have 2 sodiums over here, we'll have to put a 2 there. And now, 2 sodiums, that's happy. 2 hydrogens, and 2 hydrogens, they're happy. And then 2 oxygens, and 2 oxygens, so they're happy. So this is balanced just with a 2 there. And remember that this NaOH, that's a base. Anytime you make a hydroxide, you've made a base. So I want you to know this specific example, that we can always make a base using a metal oxide and water, because we're going to do that in lab. Now that's an important case. Now likewise, we can react a non-metal and oxygen, and this will make a non-metal oxide. And this, keep in mind, is going to be what kind of bond? Well, if it's a nonmetal and oxygen, it's a nonmetal, it's going to be covalent. So I want to look at a really simple example. Let's say we had solid carbon, and that could be, you know, a little like barbecue brick or something like that, but solid carbon, and we're going to react that with oxygen gas. And of course, Kevin is saying, don't forget the 2, Orlando, and I won't. Well, if we react those, we are going to get a non-metal oxide. Now, there's actually a few different products we should get, but you know, I know you know, in this case, the most common one. Carbon and oxygen together, what's the most common thing we get? Well, carbon's ready to make 4 bonds, each oxygen can make 2, and it really nicely makes carbon dioxide gas, which you know. You instinctively know that when we burn carbon products, we get CO2. This isn't the only product we could get, and we'll talk about that more later on. But any non-metal oxide that works would be an okay product. This is the easiest and most obvious one. But what I want to note is actually more important what comes after that. So we said that metal oxides dissolve to make bases. Well, non-metal oxides, like CO2, there's no space there. They dissolve to form not bases, but acids. And let's take a look. Again, I mention this because we're going to do this in a specific lab. Let's take our non-metal oxide, in this case carbon dioxide, and when we react this with water, what's going to happen? Well, again, we're going to have a synthesis reaction. These are going to come together. And since they're coming together, we're going to have the 2 hydrogen and carbon. And then there's 3 oxygens here, and this works nicely because this is a real thing. This is, of course, what ion? CO3. It's the carbonate ion. So this whole thing would be carbonic acid. This is just one example. If we'd had carbon monoxide instead, we'd have gotten carbonous acid. And there's lots of different examples. But what I want to know is that when we dissolve a non-metal oxide in water, we make an acid. When we dissolve a metal oxide in water, we make a base. All right? These are 2 distinctions we want to know. Again, don't stress if that seems a little bit confusing. Just note that every example we've done here is two smaller species coming together to make a single compound. These are all synthesis reactions, all things coming together. Yes, you're going to have to know what happens when a metal and an oxygen react. Yes, you're going to have to know what happens when metal oxides dissolve in water. And same with non-metal and oxygen and non-metal oxides. But you'll have lots of time to practice, so don't let it stress you out. Next, I want to look at decomposition reactions. And of course, when we say decomposition, we mean breaking apart. When something decomposes, it breaks apart. So these are reactions where a larger compound breaks down to form two or more, and in this course, it's mostly going to be two smaller species. I know I said compounds, but it won't always be a compound. Sometimes we're just going to get an element. So I should have said species, and you can change that. So let's look at a nice simple example. If I had lithium sulfide, not sulfate, but sulfide. You know that lithium takes a charge of +1, sulfur takes a charge of -2. So for this thing to work, we're going to need Li2S, lithium sulfide. Well, in a decomposition reaction, I'm going to break these apart. And to make them break apart, I've got to do something. A decomposition reaction always requires some kind of input to make it happen, and often it's just a bit of energy. Maybe a bit of heat will make the reaction start. Sometimes it could be electricity. It could be all kinds of different things, but something like that. In the case of lithium sulfide, heat will cause it to decompose. Now, the nice thing about these are they're easy. The simple ones, a binary compound like this, I've got lithium and I've got the sulfide ion. What can they possibly break down to? Well, they're going to break down to give me lithium, solid lithium, and solid sulfur. And keep in mind, neither of these is diatomic, so they're happy just like that. Okay, now the only thing left to do here is what? And of course, Caitlin is screaming, Orlando, you fool, you haven't balanced the equation. And she's right, so make sure you balance it. And we're back. And hopefully you found that, yeah, all we need to balance this guy is a 2 in front of the lithium. And there we go. Now, in general, what do these look like? Well, we have something a single compound, and it undergoes a reaction, and it actually breaks apart into two things. So something like that. Again, the letters aren't important. What's important is the idea that a single compound breaks down into smaller species. Now, these above, binary compounds, are easy. Binary compounds decompose into elements. And I could do 50 examples, but let's just keep it really simple. Lithium chloride, what is it going to form? Well, all it can form is lithium and chlorine. And of course, gotta do that. And then to balance it, 2 chlorine here, so I need 2 there. Now I have 2 lithium. I need 2 there, and I'm balanced. Does that make sense? So whenever you have a binary compound, it just breaks down into its elements, and those are super easy to work with. There are some more complicated things to know, and I'm going to give you just 2 examples, 2 special cases that I want you to know. I want you to know what happens with carbonates. And the reason I want you to know what happens with carbonates is we're going to do a lab that involves decomposing a carbonate. And let's see if we can figure it out. Let's see how clever you are. So we can pick any carbonate we want. And I am going to say, oh, I don't know. Let's say magnesium carbonate. So Mg, that of course takes a charge of 2 plus. The carbonate ion takes a charge of 2 minus. So that is happy just like that. And I should have written them a little closer to each other. So like that. So that is magnesium carbonate. And again, I could pick any example I want here. Well, if this is going to break down, do you have any guess what might be released? Now, there's no necessarily way for you to know this, but you could maybe take a bit of a guess. Anyway, if not, that's okay, because I'm going to tell you. Carbonates release CO2 when they decompose. Maybe you guessed that, which would be awesome. Let's see if you can figure out what remains if this releases CO2. This is a solid, and we're probably heating it up to make this happen. Because again, that's typically how we make decomposition happen. It's not the only way we make decomposition happen, but it's the main way. So we heat up this, and it's going to release CO2, and that's a gas. And what do you think is going to remain? Well, if we look here, the carbon's going to be gone, and 2 of these oxygens are going to be gone. So we'll be left with just magnesium and oxygen. And we may have to rebalance that, but in this case, magnesium takes a charge of 2 plus. Oxygen takes a charge of 2 minus. So this actually just works nicely, which means that this one is self-balancing. They won't all be self-balancing, but in this case, they are. So we get carbon dioxide and magnesium oxide. So here's what I want to mention. This is another case where a metal oxide forms. When you decompose a carbonate, you get CO2 and you get a metal oxide. And if you remember, those metal oxides, when they dissolve in water, they'll give you a base. So if we took that magnesium oxide and dissolved it in water, it would give us magnesium hydroxide. It would give us a base. All right, we're going to do this in our lab, which is why I want you to know this specific example. So when carbonates decompose, we get CO2, and we're left with a metal oxide. And the last example we're going to do today, the last specific one, and again, we'll see if you can figure it out, is what happens when you get a hydroxide. So I wish that I could interactively say, pick a random hydroxide, but I can't. So let's do done magnesium, we've done lithium, they're kind of boring. But I want to stay away from the multivalent metals just for now. So let's say, oh, I don't know. Let's say calcium. So let's say we had calcium, which takes what charge? 2 plus. And the hydroxide ion, which has what charge? -1. And so, of course, for this to work, we're going to need 2 of these. So if we have calcium hydroxide, which is CaOH2, and this breaks down, what's going to be released? Well, obviously, the calcium is going to be somewhere, but we have hydrogen and oxygen to release. And we have hydrogen and oxygen to release. What do you think it might release? what's a stable compound that we could release that involves hydrogen and oxygen? And if you're like me, you're thinking, I know. And if you're like, well, I don't know, let's say Kendra, she's also going, I know. Hydrogen and oxygen, it might release water. Ah, you're right. It'll probably release it as a gas because, again, we're doing this using a lot of heat. So it's probably going to release some water as a gas. But then what remains? Well, the calcium still remains. And then we've used 2 of these hydrogens, but we've only used 1 of the oxygens. So there's some oxygen left. And the nice thing, of course, calcium has a charge of +2. Oxygen has a charge of -2. So this one is, again, self-balancing, which they won't always necessarily be. And there we go. So this is the other rule I want you to know. Hydroxides release water when they decompose. Always. And again, a metal oxide remains. Now, the really keen amongst you will note that this is just the reverse of reacting a metal oxide with water and getting a hydroxide. And that is a good thing to note, that decompositions are synthesis reactions in reverse. They're the reverse of synthesis reactions. So again, I'm going to want you to know that in general, decomposition is when we take one large compound and break it down into 2. For binary compounds, for just a metal and a non-metal, that should be super easy because it forms just a metal and a non-metal. Very easy. But then there are the 2 special cases I want you to know so far. I want you to know what happens when a carbonate decomposes, and I want you to know what happens when a hydroxide decomposes. That's all for today. You've got some homework. I gave you 2 sheets, one which is intentionally very straightforward, and then the next which is a bit more challenging. So work on those, get lots and lots and lots of practice. I miss you guys, and I will see all y'all on Wednesday, which is tomorrow. So I'll see y'all tomorrow. Have a wonderful day.